National Fire Protection Association 70, National Electrical Code, Article 300, Wiring Methods 300.22c busways states that where busways are installed in other than dry locations, they shall be enclosed in corrosion-resistant enclosures. This code section does not explicitly address the need for fire stopping between bus bars within a bus duct. Institute of Electrical and Electronics Engineers C37.23 Standard for Metal Enclosed Bus, Section 8.1.1 Structural integrity states that the bus shall be supported and braced throughout its length to withstand the fault current forces prescribed in IEEE DC 37.29, and the method of supporting the bus shall be such that the possibility of misalignment between bus enclosure sections and the electrical damage caused by arcing a bus joints is minimized. Section 8.1.2 Insulation states that the bus shall have sufficient insulation to withstand the test requirements of this standard. These IEEE standards do not specifically address the need for fire stopping between bus bars within a bus duct. It is important to consult the manufacturer's instructions for the specific Westinghouse 480 volts 2000 amps bus duct installed. The manufacturer may provide specific guidance on fire stopping requirements. While there is no specific code requirement for fire stopping between bus bars within a bus duct, it is generally recognized that fire stopping is not necessary or feasible for the following reasons. Firstly, current limiting effects. Bus ducts are designed to limit fault currents, reducing the risk of arcing and fire spread. Secondly, enclosure integrity. Bus ducts are enclosed in metal enclosures that provide protection from fire and other environmental hazards. Thirdly, thermal expansion. Fire-stopping materials could interfere with the thermal expansion of the bus bars, potentially causing damage to the equipment. Based on the available information, it appears that fire stopping between bus bars within the Westinghouse bus duct is not required or feasible. To elaborate further on the principles that justify the absence of fire stopping within bus ducts, it's essential to understand the design and functionality of these systems. Bus ducts serve as a crucial component in electrical distribution systems, particularly in large facilities such as hospitals, commercial buildings, and industrial plants. Their primary function is to efficiently and safely transmit electrical power from the source, such as a transformer or generator, to various load centers throughout the facility. The construction of a bus duct involves several key elements, including the bus bars themselves, the insulating materials, and the enclosure. The bus bars, typically made of copper or aluminum, are the conductors that carry the electrical current. They are carefully arranged within the enclosure to minimize impedance and ensure efficient power transmission. The insulating materials, such as epoxy or fiberglass, provide electrical insulation between the bus bars and the enclosure, as well as between the bus bars themselves. This insulation is critical for preventing short circuits and ensuring the safe operation of the system. The enclosure, usually made of steel or aluminum, serves as a protective barrier against physical damage, environmental factors, and electrical hazards. It also helps to contain any arcs or sparks that may occur during a fault condition. The design of bus ducts incorporates several features that contribute to their fire resistance and safety. Firstly, the enclosure provides a physical barrier that helps to prevent the spread of fire. The metal construction of the enclosure is inherently non-combustible, and it can withstand high temperatures without melting or deforming. Secondly, the insulating materials used in bus ducts are typically flame retardant or self-extinguishing. This means that they will not easily ignite or support combustion, and they will quickly extinguish any flames that may occur. Thirdly, bus ducts are designed to limit fault currents, which reduces the risk of arcing and fire spread. When a fault occurs in an electrical system, such as a short circuit or ground fault, a large amount of current can flow through the conductors. This high current can generate intense heat, which can ignite flammable materials and cause a fire. Bus ducts are equipped with protective devices, such as fuses and circuit breakers, that are designed to quickly interrupt the flow of current in the event of a fault. This helps to limit the amount of heat generated and to reduce the risk of fire. The absence of fire stopping within bus ducts is justified by several factors. Firstly, the enclosure provides adequate fire protection. The metal construction of the enclosure is inherently non-combustible, and it can withstand high temperatures without melting or deforming. This helps to prevent the spread of fire from one section of the bus duct to another, as well as to adjacent areas. Secondly, fire-stopping materials can interfere with the thermal expansion of the bus bars. Bus bars expand and contract with changes in temperature due to the electrical current flowing through them. Fire-stopping materials can restrict this expansion, which can cause stress on the bus bars and lead to damage. Thirdly, fire-stopping materials can trap moisture and contaminants within the bus duct. Moisture and contaminants can corrode the bus bars and insulation, which can reduce the reliability and safety of the system. In addition to these factors, it's important to consider the practical challenges of installing and maintaining fire-stopping within bus ducts. Bus ducts are often installed in tight spaces, which can make it difficult to access the bus bars and apply fire-stopping materials. Furthermore, fire-stopping materials can deteriorate over time, which can require periodic inspection and replacement. The NEC provides specific requirements for the installation and maintenance of busways, including those located in hospitals. These requirements are designed to ensure the safe and reliable operation of busway systems, and they address various aspects such as grounding, overcurrent protection, and ventilation. The NEC also includes provisions for fire stopping in general, but these provisions do not specifically address the need for fire stopping within bus ducts. The NEC recognizes that bus ducts are designed and constructed to provide adequate fire protection, and it does not require additional fire stopping measures. The IEEE standards for metal enclosed bus also address the issue of fire protection. These standards specify requirements for the design, construction, and testing of metal enclosed bus, and they include provisions for fire resistance. The IEEE standards recognize that metal enclosed bus is inherently fire resistant, and they do not require additional fire stopping measures. The manufacturer's instructions for the specific Westinghouse 480 volts 2000 amps bus duct installed should be consulted for any specific recommendations regarding fire stopping. The manufacturer may have conducted fire testing on the bus duct and may have developed specific fire stopping requirements based on those tests. In the absence of specific fire stopping requirements from the manufacturer, it is generally accepted that fire stopping is not necessary or feasible for bus ducts. The design and construction of bus ducts provide adequate fire protection, and additional fire stopping measures can interfere with the thermal expansion of the bus bars and trap moisture and contaminants within the system. It is important to document the reasons for not installing fire stopping within the bus duct and to provide this documentation to the Joint Commission. The documentation should include references to the NEC, IEEE standards, and the manufacturer's instructions. The documentation should also explain the reasons why fire stopping is not necessary or feasible for bus ducts. The Joint Commission is responsible for accrediting hospitals and other healthcare organizations. The Joint Commission's standards for accreditation address various aspects of healthcare quality and safety, including electrical safety. The Joint Commission's electrical safety standards are based on the NEC and other industry standards. The Joint Commission surveyors are trained to identify electrical hazards and to ensure that hospitals are in compliance with the applicable standards. The Joint Commission surveyors may question the absence of fire stopping within bus ducts. In these cases, it is important to provide the surveyors with the documentation that explains the reasons why fire stopping is not necessary or feasible. The surveyors will review the documentation and determine whether the hospital is in compliance with the applicable standards. In summary, fire stopping between bus bars within a bus duct is generally not required or feasible due to the design and construction of bus ducts, which provide adequate fire protection. The enclosure is made of non-combustible material, the insulating materials are flame retardant, and the bus duct is designed to limit fault currents. Fire-stopping materials can interfere with the thermal expansion of the bus bars and trap moisture and contaminants within the system. The NEC, IEEE standards, and manufacturer's instructions should be consulted for specific requirements regarding fire stopping. The reasons for not installing fire stopping should be documented and provided to the Joint Commission. To further support the assertion that fire stopping is generally not required within bus ducts, let's delve into the specific design characteristics of these systems and how they inherently mitigate fire risks. Firstly, consider the materials used in the construction of bus ducts. The enclosure is typically made of steel or aluminum, both of which are non-combustible materials. This means they do not readily ignite or contribute to the spread of fire. They can withstand high temperatures without melting or significantly deforming, providing a robust barrier against flames. The bus bars themselves, usually made of copper or aluminum, are also non-combustible. While they can conduct heat, they do not serve as fuel for a fire. The insulation surrounding the bus bars is another crucial element. Modern bus ducts use advanced insulation materials that are specifically designed to be flame retardant or self-extinguishing. These materials resist ignition and, if exposed to a flame, will not sustain combustion. This significantly reduces the risk of fire propagation within the bus duct. Secondly, the enclosed design of bus ducts plays a vital role in fire safety. The enclosure not only protects the internal components from physical damage and environmental factors, but also contains any potential arcs or sparks that might occur during a fault condition. This containment is crucial in preventing the ignition of external materials and limiting the spread of fire. The enclosure acts as a barrier, preventing flames and hot gases from escaping and potentially igniting nearby combustible materials. Thirdly, bus ducts are designed with inherent current-limiting characteristics. Electrical faults, such as short circuits or ground faults, can generate extremely high currents, leading to intense heat and potential fire hazards. Bus ducts are equipped with protective devices, such as fuses and circuit breakers, that are specifically designed to quickly interrupt the flow of current during a fault. This rapid interruption limits the amount of heat generated and significantly reduces the risk of fire. Moreover, the physical configuration of bus bars within the enclosure contributes to the overall fire safety. The spacing between the bus bars and the enclosure walls is carefully engineered to minimize the risk of arcing and flashovers. The design also promotes natural convection, allowing heat to dissipate effectively and preventing the buildup of excessive temperatures. Now, let's address the concerns about thermal expansion and contraction of bus bars. As the electrical current flows through the bus bars, they generate heat, causing them to expand. Conversely, when the current is reduced or shut off, the bus bars cool down and contract. This thermal cycling can create stress on the bus bars and the surrounding components if not properly accommodated. Fire-stopping materials, if installed between the bus bars, could restrict this natural expansion and contraction, potentially leading to mechanical stress, deformation, and even failure of the bus bars. This is a significant concern, as any damage to the bus bars could compromise the integrity of the entire electrical system. Furthermore, fire-stopping materials can trap moisture and contaminants within the bus duct. Moisture can lead to corrosion of the bus bars and insulation, while contaminants can reduce the effectiveness of the insulation. Both of these factors can increase the risk of electrical faults and reduce the overall reliability of the system. The NEC recognizes the inherent fire-resistant properties of properly designed and installed bus ducts. While the code provides general requirements for fire stopping in buildings, it does not mandate fire stopping within bus ducts. This is because the NEC acknowledges that bus ducts, when installed in accordance with the manufacturer's instructions and relevant standards, provide an acceptable level of fire protection. The IEEE standards for metal enclosed bus reinforce this position. These standards focus on the design, construction, and testing of bus ducts to ensure their structural integrity, electrical performance, and fire resistance. The IEEE standards do not require fire stopping within bus ducts, as they recognize that the inherent design characteristics of these systems provide adequate fire protection. It's also important to consider the practical challenges of installing and maintaining fire stopping within bus ducts. Bus ducts are often installed in confined spaces, making it difficult to access the bus bars and apply fire-stopping materials effectively. Moreover, fire-stopping materials can deteriorate over time, requiring periodic inspection and replacement. This can be a costly and time-consuming process, especially in large facilities with extensive bus duct systems. In conclusion, the absence of fire stopping within bus ducts is justified by a combination of factors, including the non-combustible materials used in their construction, the enclosed design that contains potential arcs and sparks, the current limiting characteristics that reduce the risk of fire, and the need to accommodate thermal expansion and contraction. The NEC and IEEE standards recognize the inherent fire-resistant properties of bus ducts and do not require additional fire-stopping measures. Therefore, it is reasonable to assert that fire stopping between bus bars within a Westinghouse bus duct is not required or feasible based on the available information and industry best practices. When communicating this information to the Joint Commission, it's essential to present a clear and concise explanation of the factors outlined above. Provide documentation from the bus duct manufacturer, the NEC, and the IEEE standards to support your position. Emphasize the inherent fire-resistant properties of bus ducts and the potential drawbacks of installing fire-stopping materials. By presenting a well-reasoned and evidence-based argument, you can effectively address the Joint Commission's concerns and demonstrate compliance with relevant codes and standards.